In this lecture, we are going to discuss grammars. A grammar G, capital J, is defined by four tuples G equal to VTPS, where V is finite non-empty set of objects called variables or non-terminals. T, finite non-empty set of objects called terminals. P, set of production rules. And S is a special symbol called the start symbol. Now, for a grammar, this P, that is the set of production rule, this is the most important component for any grammar. This P has the general form x derives y, where this left hand side, that is x, can be either variable or terminal symbol, but it cannot be null. So put a plus sign here, V union T plus. Now, the right hand side of this production rule, that is y, it can be either variable or terminal symbol including null. So we put a star here. So this is the general form for any production rule. Left hand side, right hand side, variable or terminal symbol without null. Null cannot be this side. Variable or terminal symbols, any combination including null. Now we take an example. Suppose in our example G equal to, this is our V, that is this is our terminal symbol T, production rule P, and S here S, start symbol. Our production rules, they are given as S can be ASB and S can be null. This is production rule 1, this is production rule 2. Okay. So these four tuples are defined here. V is our capital S, terminal symbol they are A and B. Production rules, there are two production rules, and S is our start symbol. Now, by convention, the variables or non-terminal symbols, they are written in capital letters, and terminal symbols, they are mentioned in small case. So let's see what are the strings this grammar is going to derive. First of all, starting from the start symbol S, we take the production rule 1. So S can derive ASB. Now again, we apply the production rule 2. So this S become null. So A null B. And we know the concatenation of any symbol with null results in the same symbol. So AB can be derived by this grammar. Now, what are the other strings which can be derived by this grammar? Now, the other strings which can be derived by this grammar. Suppose we apply the production rule 1, ASB, and again we apply the production rule 1, it becomes AASBB. Then we apply the production rule 2, which says S can be replaced by null. So null here. So this string AABB can be derived. Similarly, S can be ASB, S can be AASB and B. Again, by applying the production rule 1, AAASBBB, and finally S can be null, so AAABBB can be derived. Now we can notice one thing. In all the strings which can be derived by this grammar, the number of A's and number of B's, they are equal, and A comes first, then B. So can we write the strings derived by this grammar in a general form? After a few trial, we can see the number of A's, they will be always equal to number of B's. So we write A to the power n, B to the power n, because they are same. And the production rule 2 says null can also be derived. the very first time if we apply the production rule, S can be null, so null can be derived. So we put n greater than equal to 0. Why this equality equal to symbols is here? Because S can be null. So if we put n equal to 0, it becomes a to the power 0, b to the power 0, which is nothing but null. So our grammar derives all strings which are in the form of a to the power n, b to the power n, such that n greater than equal to 0. This is our first example for grammars.